All right, good morning, everyone. Can I get you to open up your books to the problems dealing with calculating photon energies, or energy quanta, we call them. These are the problems from your textbook. So just get them out to see if you have any questions that we'll get to in a minute. But I want to spend the first couple of minutes just reviewing some things here. How we arrived at these two formulas was a little bit of a journey. But in the end, what I would say to you is it's very, very important that you're able to calculate the energy of a photon of light. One of the things that came out of Planck's work, and Planck did the work he did in order to solve a problem called the blackbody radiation problem. One of the things that came out of it was that energy is quantized. And what that means is energy, under certain circumstances, is not fluid. It's not just any kind of amount you choose to want. It's chunked. And in the case of light, what came out of this is light energy is chunked. We can call it particles of light, but don't be deceived into thinking that those particles of light have mass. They do not have mass. All it means is that if you had a tap, a light tap, a dimmer switch, where you could open up the tap and allow light to leave, if you open up the tap a little bit, nothing will come out. And if you'd open it up a little bit more, what will happen is you'll just get this little lump of light energy that comes out, this little chunk of light energy. And if you open it up a bit more, what you would discover is just like a water tap would drip drops of water, this is going to allow chunks, I don't want to call them drops, but chunks of light energy to come out. The difference with water is, of course, you can take a drop of water and tear it apart into different pieces. This chunk of light energy, which we call a photon, is not divisible. And each color or frequency or wavelength of light has a given energy by these two formulas, where the energy of the photon or quantum of light energy is Planck's constant times the frequency, or it's equal to Planck's constant times the speed of light over the wavelength. And Planck's constant can be expressed in joule seconds, and you'll want your formula sheet out here as we go through this. When you look at your formula sheet for Planck's constant in joule seconds, it's 6.63 multiplied by 10 to the negative 34 joule seconds. That's joules times seconds, not joules per second. It's joules times seconds. Or if you want to work in electron volts, you can use the form 4.14 multiplied by 10 to the negative 15, and that's electron volt seconds. And the idea here is that the wavelength of radiation and the frequency of radiation and the energy of a photon of that radiation are all tied together in terms of these formulas. So if you have the energy of a photon and you want to find the frequency, you can use E equals HF. If you have the energy of a photon and you want to find the wavelength, you can use E equals hc over lambda. And certainly if you have the wavelength or the frequency, you can calculate the energy. We've already discussed the fact that you can find the wavelength from the frequency or the frequency from the wavelength. The result is when you calculate energies of photons for different wavelengths, you get different energies. And here are some typical energies. A violet photon of a particular wavelength might have 3.1 eV. Blue might be 2.7. Lime might be 1.9. You understand, though, that if I take this blue photon of energy, or light, and I go to a slightly shorter wavelength, which would be a higher frequency, I'd get a different photon. It would have more energy. So when we talk about white light, there's just scads and scads and scads of different photons for each wavelength. Let's do some calculations together here, just as a warm-up. I would like everybody to find the energy of a 500 nanometer photon, which is reddish, kind of orangey probably. Pardon me. It's probably green. Find the wavelength of the energy of a 500 nanometer photon, and I want you to find it in electron volts. So I will give you a head start here. What you're going to do is you're going to use the energy of the photon as hc over lambda, and some of you might choose to calculate it in joules and then convert it to electron volts. Some of you might choose to just go straight to electron volts by using the 4.14 times 10 to the negative 15. And I'm going to show you both methods up here. I'm not going to do my work on the screen, though. I'm just going to do it on my calculator. So if I take 4.14 multiplied by 10 to the negative 15, that's Planck's constant times the speed of light. And I divide by the wavelength, which is 500 nanometers, which is 5 times 10 to the negative 7 meters. So there's Planck's constant times the speed of light divided by the wavelength. I get this many electron volts. If you choose to use 6.63 multiplied by 10 to the negative 34 times the speed of light, and then divide by the wavelength, this number is in joules, and since 1 electron volt is 1.60 times 10 to the negative 19 joules, if I divide this by that many joules, I get 2.486 electron volts. And I'm doing this exercise for a number of reasons. The first one, and it's not that big of a reason, but it's important, is that the 6.63 times 10 to the negative 34 joule seconds and the 4.14 times 10 to the negative 15 eV seconds are not exact conversions of each other. If I take 6.63 multiplied by 10 to the negative 34, and this has units in it of joules somewhere, and I divide by the number of joules per electron volt, I don't get exactly 4.14. I think you get 4.136. Well, 4.1375. So these numbers that are on your formula sheet have extra digits to them that end up being truncated or rounded off or clipped off when we round to 3 significant figures. So you're not going to get the exact number depending on which method that you use. And there's something to be learned from that, that particularly with today's stuff, if you're doing a problem and you get a slightly different answer, that's okay, depending on the path you chose. I'm going to go with the 2.48. EV. Did you get 2.48 when you used the Planck's constant with EV? Okay. Now, what if I told you we had a 1.8 electron volt photon? I would like you to find the wavelength in nanometers. So that means you're going to take this formula, flip it over, mathematically speaking, to get this, and we can calculate the wavelength. And look, since we know it's 2.48 eV, we'll use the 2.48 eV, and we'll use Planck's constant in electron volts. So if I take Planck's constant in electron volts, 4.14 times 10 to the negative 15, I multiply by the speed of light, and then I divide by that 2.48 eV, I get 501. Yep. Oh, it actually tells you 1.8. Thank you. I thought we were doing, my mistake. We're doing 1.8 eV. We're not calculating the wavelength from the 2.48. Thank you, Annalie. So let me redo that. And we're dividing by 1.8 eV. My mistake. And we get, how many nanometers is 6.9 times 10 to the negative 7 meters? Miles? Sorry? 690 nanometers. Now, what I would like you to do, so does anybody have any questions on those calculations? And my mistake, I thought we were working backwards here. What I would like everybody to do is multiply this number and this number. You should get 1242. I would like you to multiply this number and this number. You get 1242. And my point is that for any photon, whether it's visible light or infrared or ultraviolet or any photon on the electromagnetic spectrum, the energy in electron volts multiplied by the wavelength in nanometers is always going to give you 1242. The units would be electron volts times nanometers. And this becomes a very useful thing. What this is saying, if you look at this formula of E equals hc over lambda, is when you multiply both sides by lambda, you have to get 1242, which means hc is 1242 eV nanometers. And because we so often go from nanometers to electron volts or electron volts to nanometers, this becomes very useful. I really had to bite my tongue last week and not do this, but if I were given this question 1, and if you're given it from now on, you'd probably just go 1242 divided by 500. And that's how many nanometers it is. If I wanted to find out how many nanometers a 1.8 eV photon is, I would go 1242 divided by 1.8. I get 690 nanometers. It's a very efficient way to calculate things. And by the way, if I take 1242 divided by 500, if I did want an energy in joules, I can just convert that to joules. It's a very slick, quick way of finding energy from wavelength or wavelength from energy. And we're going to be seeing this again and again. When we get into Unit 4, there will be a problem that we work on that involves finding at least 18 energies of 18 photons. And if you do it using the 1242, it's really simple. If you do it any other way, it's a lot of work. Okay. All right. Now, does anybody have any questions you would like me to go over from the textbook? Go ahead, Lynette. 708, question 2. Certainly. So how many 400 nanometer blue light photons per second are required to deliver 10 watts of power? So try to remember, please, that what I told you on Friday. First of all, I would rather you write the word watts than a capital W. Okay, I think the unit is a very special unit. That you remember this is 10 joules in 1 second. So if we're asked how many of those photons are required in 1 second to deliver that much energy, the question really becomes how many photons, how many 400 nanometer photons have a total energy of 10 joules. And I hope you're starting to get more familiar, everybody, with the energies of photons. Visible light photons have energies in the 10 to the negative 19 joule range. Very tiny. So the concept of a 10 joule photon, if I go back and take a look at this, if I convert this to joules, we're talking about 2.4 times 10 to the negative 18 joules. No. times 10 to the negative 19 joules. Can you confirm, everybody, that 1.5 electron volts is that many joules? What you're doing, and I hope you're getting more and more used to this, is saying that 1 electron volt is 1.6 times 10 to the negative 19 joules. So you're multiplying that by 1.5. And I think you get 2.4. Okay. If I do the same thing here for the violet end of the spectrum, and I'm just converting this visible light photon in eV to joules, I get 4.96 times 10 to the negative 19. Is that right? Okay. So when we talk about visible light photons, their energies are very tiny, right? Which is one of the reasons why we would prefer just to say 3.1 eV. It's a nicer number to think about. When you get into X-ray photons, you're not going to be in the joule range. You're still going to be 10 to the negative something joules. So why am I going over this? Because the question that Lynette is asking about requires that we have 10 joules of energy. And I want to impress on you that the only way you're going to get 10 joules of light energy is by having a large number of photons, because each photon is really tiny. Let's calculate the energy in joules of 1 photon. Now, this is how I will do it. I will take 1242 divided by 400, and that's eV. I will convert that to joules. I'm not actually using the hc over lambda formula here. What somebody else may decide to do instead is use E equals hc over lambda, and since we want it in joules, they will use Planck's constant that has joules in it. So they will take 6.63 times 10 to the negative 34, multiplied by the speed of light divided by the wavelength. Now we get slightly different answers, okay? And this is what I was talking about before. It's not important. What's important is that energy that we're looking at here, Lynette, is the energy of 1 photon, 4.97 multiplied by 10 to the negative 19 joules. And we want to find out how many of those little itty-bitty photon energies are required to give us 10 joules. So what we can do is set up a ratio and say 1 photon is 4.97 times 10 to the negative 19 joules. That has to equal x photons over 10 joules. And again, I think there's probably a large population of Physics 30 students that just know what to do without writing out the ratio. You understand that you're going to take the total energy divided by the energy of 1 photon. And you're going to get about 2 times 10 to the 19 is by my count. Yeah. Just one final note before we get started with today's lesson. This is very similar to my mind is drawing a blank. We've encountered this before. I know where we've encountered it with Young's double slit formulas, where if you use the good formula when you're allowed to use the lousy formula, you get a slightly different answer. Remember that? So if you're writing a multiple choice exam question, it's possible that you decide to be clever, and I'm not being sarcastic, you decide to be clever and use the formula that always works. But what you discover is you get an answer that's slightly different than one of your choices. You need to be intelligent enough to realize it's because of a rounding thing. And the same thing here. Depending on which version, which method you use to get there, you might get a slightly different answer. Okay. So we're going to move on today and look at what's called the photoelectric effect. Usually this is 3 days. Usually we spend 3 days on this. And that's probably going to be the case again today. I always have these ambitions of somehow getting it down to 2 days, but it never really seems to come to fruition. On some diploma exams, out of, say, 40 questions, pardon me, I think 50 questions. I have to look. I don't know why I don't remember. You might see a total of 10 questions relating to photons, the photoelectric effect. That can be close to 20% of the exam. This is a really important unit that we're in right now in terms of this topic. So the photoelectric effect is what we're going to be spending some time on. I want to start by saying that you should understand whatever the photoelectric effect is. When you do calculations, you're really using the law of conservation of energy. During the photoelectric effect, energy is always conserved. Okay? We're going to start off by learning what the photoelectric effect is, and along the way we're going to see what the effect of changing the intensity or the frequency of the light used in the photoelectric effect has on what the photoelectric effect is. First of all, and this is in your notes later, so you don't need to write it down, but intensity is brightness of light. So if I were to double the intensity of the light that's shining on a surface, what I'm doing is I'm doubling the amount of light that's on that surface. So if you're looking at light from a spotlight on a stage on an actor, and I swing one spotlight and it hits that actor's face, there's a certain brightness or intensity of the light. But if I shine an identical light on the actor at the same time, then that actor is being exposed to twice the light. We say it's twice as bright, it's twice the intensity. And this isn't just a point of interest, it's a point of importance. You need to know what intensity of light means. Frequency of light, of course, refers to, in a roundabout way, the color of the light. So if I go from, say, orange light to green light, I've increased the frequency. And there's a big difference. It's easy to confuse intensity with frequency. They mean totally different things. So we're going to start off by just talking about what the photoelectric effect is. What the photoelectric effect is, and this was discovered by Hertz, is that if you have a light source that shines on a metal, and in your notes it says a high frequency light source, and the metal was zinc, the zinc becomes positively charged. That's what Hertz discovered. So you have a piece of zinc sitting there, you shine light on it, and as long as the frequency is high enough, you will positively charge the zinc. The important thing to know about light is light doesn't have a charge to it. So the inference here is that the light is hitting the metal and kicking electrons off of the metal, making it positively charged. And that, everybody, is the photoelectric effect. The photoelectric effect is taking light, shining it on a metal, and getting electrons coming off. And the key to that understanding is right in the word photoelectric. Photo has to do with light. That's why we use the word photon for light. And electric has to do with electrons. This is a diagram. This is from your textbook. He used an ultraviolet light source. I know that doesn't look like a light source. It almost looks like a fan, but that's what many UV light sources look like. That light hits a zinc plate. The zinc plate is electrically connected to an electroscope, and the electroscope shows that we end up having a positive charge. I just want to be very picky here. There's nothing about this picture that tells you it's positive. You would have to do an experiment with maybe rabbit fur and a plastic rod to determine the charge on the electroscope. So a quick question for you. If we were to shine an ultraviolet light source on a negatively charged piece of zinc, what will happen? Well, the zinc is charged negative because it's got a bunch of electrons on it. The UV light causes electrons to be ejected. What's going to happen is the electroscope will discharge. Those electrons that are causing it to have that negative charge are going to be kicked off. Every time some more of the light hits the metal, more of the electrons are kicked off. So that's what the photoelectric effect is. Now let's start talking about some details of the photoelectric effect. A fellow by the name of Robert Millikan did a lot of experiments, and we're going to encounter Millikan's name again later in the next unit. A lot of experiments with the photoelectric effect. And he wanted to he was curious about what's going on. That's the bottom line. So he used this apparatus. And this is in your notes. There's a nice big diagram there. This is called a phototube. The plate on the right is the metal plate that the light is hitting, and the light is going to be ejecting electrons. And this is connected to a power supply. You should make a mental note that this power supply is a very low voltage, like 1/10 of a volt even. I don't think you even need a voltage attached at this point, but your textbook and most textbooks will always say there's a voltage here. And what we're told in textbooks is the reason why we have this voltage is because the electrons are ejected, and you can see the electrons streaming across. Those electrons are drawn laughably large, aren't they? They're invisible. They're so tiny you can't see them. The idea here is that we attach this to a voltage to, quote, guide the electrons so they make it to the other side, where they go through the power supply and through an ammeter back to here. By the way, if it's not obvious, this is what a solar panel does. A solar panel has a whole bunch of these phototubes in it. So when it collects the sunlight, it generates a flow of charge. And that flow of charge isn't used to light a light bulb right away. It's usually used to store electrons in a battery. And then you have an array of batteries that you run all of your electrical devices off of. This ammeter is something that measures current. And if it's reading 0, then no electrons are going through. If it is reading a current, then it's telling you that the photoelectric effect is happening. Sometimes that current is called a photocurrent, but the most important thing, there's a lot of qualitative aspects to the photoelectric effect. One of them is this: the greater the current, the more electrons are flowing. So if you do a photoelectric effect experiment where you get an ammeter reading of 3 milliamps, and then you repeat the experiment with a different set of circumstances and you get 12 milliamps, the second trial has more electrons flowing, which means it has more electrons being kicked off of that plate on the right-hand side. So the ammeter is telling you, if you have a non-zero reading, that the photoelectric effect is happening, and the greater the current, the more electrons are flowing. So what did Millikan discover from this? The first thing he discovered is that the photoelectric effect does not always happen. The photoelectric effect will only happen if the frequency of light that strikes the metal is bigger than some value. Okay? And we call that value the threshold frequency of the metal. Now I'm going to hand out a bunch of diagrams, and I printed this separately because I wanted to print them in color, and we'll be referring to some of these diagrams, well, all of them throughout this lesson. But there's going to be certain things on these diagrams I do not want to discuss until the end of the lesson, when we're finally done putting this all together. So this minimum frequency that you need, every metal has its own special frequency. We call this the threshold frequency. Threshold is a word that means it's a boundary. So a threshold of a door is where you enter the house. So on the top of this first diagram that I've given you, or the first graphic that I've given you, it says when light is incident on a metal surface, electrons are ejected from the metal. That's what the photoelectric effect is. The light must have a minimum frequency, and it's called the threshold frequency of the metal. And I don't know why I've lost all my colors here. Give me a second to get them back. Yours has colors, correct? I think I know why that happened, but I'm not going to worry about it. We'll go here. No, we'll go here. So if I have a particular metal whose threshold frequency F sub 0, this is at the bottom of the screen, happens to correspond to this on the electromagnetic spectrum, to this blue color, that means any light shining on the metal that's over to the left, the photoelectric effect won't happen. Any frequency of light that falls in the area on the right, the photoelectric effect will happen. So this might be a diagram showing the circumstances necessary for sodium metal. But copper metal might have a threshold frequency that is here. And if copper metal has a threshold frequency that's there, then the blue light will no longer cause electrons to be ejected from the copper like it was causing electrons to be ejected from the sodium. Are you with me? Just so you know, for you who's in Chem 30 right now, you guys done electrochemistry, your redox reactions and all of that. So you know that certain elements like potassium or cesium or francium is a really volatile one, will lose their electrons very easily. They have very low threshold frequencies. It doesn't require much to nudge those electrons off, which is why you don't make jewelry made out of sodium. You're asking for trouble. Copper might be over here. Well, if copper is there, it's why copper jewelry sometimes tarnishes quite easily. Has anybody ever worn copper jewelry? Sorry?
Like it goes green?
Yeah, it goes green. And sometimes your finger goes green. I had a copper ring that I made in shop in high school, and I was very proud of it, and I wore it, but then my whole finger, and it started spreading throughout the whole finger, it turned green. So it's very reactive, whereas things like gold, like silver would be here, gold would be here, platinum would be there. And by the way, this extends outside of the visible light range, and I've drawn the infrared photons and the ultraviolet photons as not having color at all. There is more information on your diagram below, but that's we'll get to later. I just want you to know that you need a minimum frequency for the photoelectric effect to happen. That's one thing he discovers. What else does he discover? He discovers that if he makes the light brighter, so he still uses the same color or frequency, but he makes the light brighter, the current goes up. And if the current goes up, and notice this first sentence, once the photoelectric effect was achieved, I'm telling you the frequency is greater than the threshold frequency. Once that happens, if you increase the intensity or brightness or amount of light, you get more electrons being ejected. And that's shown to you in this second graphic that I've printed out for you. So that intensity again is the brightness. We've already talked about this. And the more bright the light is, or the more intense the light is, the more light is physically hitting the metal. Okay? And I'm going to leave that up on the right-hand screen while I go to the next page. I don't know that you need to write it down, but I see some of you are. I don't think you need to write it down because when you look at the next page, we've got green light hitting the metal on the left, and when you look at the right-hand side, you have green light hitting the metal, but there's twice as many beams of light. That's my way of telling you that we have twice as much light hitting the metal. And if you were to look at these blue dots, which I'm using to represent the electrons that are kicked off, and by the way, they're kicked off perpendicular to the surface in the photoelectric effect, and you look at the electrons being kicked off later, when you have a greater brightness, you see there are twice as many electrons. And that's the second thing he discovered, is that when you increase the brightness of the light, you end up getting more electrons. So there happens to be some direct connection between how much light hits the metal and how many electrons you get. So if you have a solar panel that's connected to a battery that's being charged, and then you put another solar panel next to it and you connect that as well, you're going to be collecting twice as much charge because it will collect twice as much light. Once again, there's something below that we don't need to worry about just yet. We'll get to at the end. So now he changes things. And I want you to take a look carefully at this diagram and take a look at the diagram on the first page of the handout. And they're different. They're subtly different. Lynette, do you see the difference? Right. I've switched the polarity of the potential difference. Now, I have the voltage that's been reversed. See, before, this was negative and this was positive, and the rationale for that, which I don't buy, it's more complicated than this, but the rationale for having it the way it was in part one was to help the electrons make it to the other side. But I've told you the truth, you don't even need that voltage. But I'm sticking with your textbook. Now, that polarity has been reversed. So there's some place on this power supply, a little switch, a little toggle switch. You just click it and it flips the other way. Okay, it's not a big deal. So that potential difference now is acting against what the electrons are trying to accomplish. If you get a current here, if you get a current down here, then electrons are making it through despite the fact that they're repelled from the negative on the right and they're attracted to the positive on the left. They have enough energy to make it through despite that opposition. And some students say, well, how do they make it across if they're forced backwards? And I would say to you, how does this deck of cards make it to the ceiling if gravity is pulling it down? I just have to give it enough kick upwards to make it happen. And that upwards kick, compared to the kick of the electrons, is a measure of how much energy the electrons have. If the energy of the electrons is big enough, they can make it through, and you will see evidence of the photoelectric effect. If they don't get very much energy, then it's kind of like that, right? I can give this deck of cards some energy towards the ceiling. Energy isn't a vector, but you get my drift. But it doesn't make it to the ceiling. This voltage is acting to slow the electrons down, and it's called the retarding voltage. And I know everybody kind of smirks and giggles. There was a time when the word retarded and retard and retarding didn't mean what you think they mean today. A person was called retarded because they were physically and mentally slowed down in their development. To retard something is to slow it down. So this is a voltage that acts to slow down the electrons. It's called a retarding voltage. Once the photoelectric effect is achieved, so Millikan doesn't even worry about that voltage. He shines light on the metal, he looks at the ammeter, he sees an ammeter reading, he goes, okay, we got the photoelectric effect happening. Then he starts to increase this retarding voltage. And This is a counterintuitive thing. As that voltage goes up, the current is going to go down, because the voltage is essentially going to be stopping the electrons more quickly from getting across. It's very complicated, and what we're doing here is maybe oversimplified. Put your phone away, please. But the bottom line is, what happens is as the voltage goes up, you get a smaller current, because the voltage is acting to reduce the current. When you reach a voltage, a retarding voltage that physically stops all of the electrons, we call that the stopping voltage. And it would be at that point, well, I'll ask you, how would Millikan know that he has stopped the electrons?
The ammeter won't go back and forth anymore?
No, and it won't even move at all. It will just be sitting at zero. So what happens is as you increase the voltage, the current is going to go down, and it's going to go down and down and down, and at some point it will just reach zero. And that voltage that you've hit is called the stopping voltage. So if you did the photoelectric effect experiment and you used a retarding voltage of 0.2 volts, you might get that current. If you tried 0.4, you might get this current. And you would continue to gradually increase the voltage. And at this point, we've got 0.03 milliamps. We get 1.12. If it is 0.007, this is not the stopping voltage yet. If we go to 1.23 and we get that, that's not the stopping voltage. 1.24 in my hypothetical experiment gives you 0.000 milliamps. 1.24 volts is the stopping voltage. Before I go on, I had mentioned to you that the electrons will make it across if they have enough energy. Remember me saying that? Okay. I hope you see that the amount of energy they need to make it across is related to the stopping voltage. In other words, everybody, if I had in an experiment a stopping voltage of 1.24 volts, and then I have in a different experiment a stopping voltage of 2.68 volts, the electrons in the second experiment must have had more energy when they left that plate. So the kinetic energy that the electrons have here will be smaller than the kinetic energy they have here. So what Millikan has done is devised a way to determine the kinetic energy that the electrons have when they are kicked off of the metal. This is just a diagram showing what the graph would look like in case you see it on an exam. Sorry, I thought I unfroze that other monitor. So, if the threshold frequency is exceeded, this is what he discovered, then what he realized or did or discovered was if you continue to increase the frequency, each electron gets more energy. So, when he did this experiment, I'll go back to this. If he does this experiment with green light, and he discovers the stopping voltage is this number, if he repeats it with blue light, the stopping voltage is more, because the electrons have more energy because we used a higher frequency. You can calculate the kinetic energy. So this is the first formula with the photoelectric effect. You can calculate the kinetic energy by taking the charge of an electron times the stopping voltage. Now, the reason for that is that the definition of voltage is change in energy over charge. And if you cross multiply here, if you're talking about an electron that originates on the right-hand side of your diagram, and then is stopped as it reaches the plate on the left, then the change in kinetic energy is the energy it had when it left, and this voltage is called the stopping voltage. You go back to that other handout. Here's a pictorial of what I'm talking about. This would be one page in. As long as the frequency is more than the threshold frequency, then as you go to a higher frequency, you get electrons that are moving faster. They have more kinetic energy. So we have 1, 2, 3, 4 beams of orange light striking the metal here, and we get 1, 2, 3, 4, 5, 6 electrons streaming off. I hope you understand it's probably more than 6 electrons. Just a graphic. I still have on the right 4 beams of light, so I'm using the same amount of light. It's just as bright, which means I get the same number of electrons. But green light has a higher frequency, and the idea is these electrons have more energy. What in that diagram is telling you the electrons have more energy? Yeah.
But the lines are longer?
The lines are longer, that's all. I'm trying to communicate that they're moving faster. Before we go on, I would like us just to informally do a quick calculation here. The first thing I want you to note, though, is that this only works in standard units. Which means joules. So we've got this formula, and this is actually on your formula sheet. And I'm going to tell you the stopping voltage is 1.24 volts for a particular photoelectric effect experiment. A particular metal, a particular color of light. And what I would like you to do is calculate the kinetic energy. I'll talk about the word max later. It's unimportant. I would like you to use this formula to calculate the kinetic energy that each electron will have because of that stopping voltage. So I'm just asking you to multiply the charge of an electron times that stopping voltage. And you get 1.984 times 10 to the negative 19 joules. Now what I would like everybody to do, and this is something, your phone away please, this is something that you should know how to do by now. I introduced this way back in Unit 2, this idea of electron volts and joules, but we've been working on it for a couple of days now. I would like you to convert this many joules to electron volts of energy. Since 1 electron volt is 1.60 times 10 to the negative 19 joules, you would have to take that number of joules and divide by 1.6 times 10 to the negative 19. Well, you get 1.24 EV. Well, it's not a coincidence that the stopping voltage number is the kinetic energy in electron volts. And for that reason, personally, I will never use this formula. If the stopping voltage is 1.24 volts, the kinetic energy is 1.24 electron volts. And if I wanted to know what it is in joules, I'd convert those electron volts to joules. Which, you know, I guess I'm multiplying by cube, but I'm not really multiplying by coulombs. Okay, what Millikan also discovered, this is really important, is it didn't matter the metal used. If he repeated the experiment over and over again for a particular metal, using more frequency and using the stopping voltage to calculate the kinetic energy, he would get a line that would be parallel to a line for any other metal. Okay? And by the way, where this line intersects the x-axis is the threshold frequency. I'm going to just take a breather here with you and forget about this lesson and go back in time to Friday. You remember Planck figured out, along with Einstein, that light must consist of photons whose energy is quantized. Are you with me on that? Do you remember me vague memory, me saying Planck didn't like this idea? The reason is, if energy is quantized, and I don't want to get into a big discussion, but I think this is curiously important, energy a lot of the time is related to location. So if you have a pendulum that's swinging, its energy is related to the height of the pendulum. A pendulum has a frequency, which means when a pendulum loses energy, according to Planck, it loses it in lumps. Which means it goes from having this much energy to this much energy instantaneously, which means the pendulum goes from being in one position to being in a different position without being in between. It can't be in between. Because if it's in between, it's bleeding energy. It's draining energy slowly. It's got to lose it in a lump. And that's what bothered Planck about this. He didn't think there would be anything in the real world that would correspond to this outside of that black body curve. But when you find the slope of this graph, it's Planck's constant. And that's also important for you to know about this graph. And if my graph is given in joules as a function of frequency, my slope will be Planck's constant in joules. So it turns out that Planck's constant does appear in the photoelectric effect, which means, everybody, and I'm going to talk more about this in the coming days, you cannot explain the photoelectric effect without talking about photons. The particle model of light is what's required to explain the photoelectric effect. I'm going to pause there before we get to the explanation of what's going on, which was proposed by Einstein, and it's what Einstein won a Nobel Prize in physics for, and ask, does anybody have any questions at all so far about what we've covered? Ian?
Why is slope, if the slope is rise over run, we have the joules over frequency, why is the units for slope joules times?
Because hertz, frequency is measured in hertz, and what a hertz is a per second. So when I say the frequency of a hummingbird's wings is 100 hertz, that means it's 100 per second. I mean, it's 100 flaps per second, but flaps is not a real unit that we use in science. So hertz, by definition, has frequencies of 1 over seconds. In fact, very often in textbooks, and if you go on and take post-secondary physics, you'll be told, oh, the frequency of the light is 4.0 times 10 to the 14, and instead of saying hertz, they will say this. They will say seconds to the negative 1, which means over seconds. Now, getting to your question, if your slope is rise over run, that means it's change in kinetic energy over change in frequency. And by the way, with your lab, these deltas here that you did on the lab you got back today, those are important. Slope is not energy over frequency. It's change in energy over change in frequency. We would have joules over the reciprocals of seconds, and that turns into joules times seconds. Any other questions with regards to anything we've done so far? All right, so a good explanation of what's going on has to be able to explain everything. Why, when you shine more light, do you get more electrons coming off? Why does the photoelectric effect not happen until you reach a certain frequency? Why, when you reach that frequency, do the electrons come off with more energy as you increase the frequency? And Einstein is the fellow who came up with the explanation. The first thing you have to appreciate is light is quantized. Light consists of photons. There's no way to explain the photoelectric effect by talking about electromagnetic waves. It just doesn't work. Secondly, we already know this, the energy of a particular quantum of radiation, which we call a photon, can be found using Planck's hypothesis, E equals hf or hc over lambda. So when you shine red light down on a metal, you have a bunch of little tiny red photons hitting the metal, raining down on the metal. When you have green light shining on the metal, you have a whole bunch of green photons, which are still really tiny bundles of energy, but they're more energy than red. I will very often say a green photon is bigger than red. I don't mean physically bigger. So maybe it's important for you to appreciate that when I draw this diagram here and all these photons, I'm not saying they're bigger, I mean they have more energy. You get my point here? Okay. So, Einstein says that all of the light hitting the metal consists of photons, and you can calculate their energy using that. Each photon hits one electron. We've done further experiments since then. Well, I haven't been involved, but they have done further experiments since 1910, 1905 when they did this, that proves definitively, for some weird reason, that an electron sitting on the surface of the metal will only absorb one photon. It cannot absorb 2 or 3 or 4. It only absorbs one. For some reason, when the electron leaves the metal, it cannot absorb another photon. So it's a one-to-one interaction, which, by the way, explains why when you shine more light on the metal, you get more electrons coming off. Because more light means more photons. More photons means more electrons absorbing the photons. When a photon makes contact with the metal, a single electron absorbs the photon. I have a question for you. What does that mean to say that the photon is absorbed by an electron? Like, if I say a sponge absorbs water, the water is in the sponge, right? It's not what's happening here. What does it mean?
The energy is transferred to the electron, so it probably starts moving faster.
The electron does.
Yes.
So where's the photon?
Well, it does not have mass, I don't think. So since it's basically just energy, it's just become energy for the electron.
In other words, perfect. A photon is just energy. That's what a photon is. It's pure energy. If it's absorbed by the electron, then the electron just has that energy. Where's the photon? It doesn't exist. The photon is gone from the universe. Its light energy is now owned by the electron. The electron has this newly found energy. So the photon no longer exists. So this is conservation of energy. The electron now has that energy that the photon had. Okay. I'm going to go a little off script here. Would you agree that the electron that absorbs the photon is attached to an atom in the metal? So if I were to attach a coin to this table, I put a little bit of glue there, a little tiny dab of glue, and I put a coin on the table. Will any amount of energy be able to remove the coin? Like I just blow on it. Is that going to be enough energy to remove the coin? No, it's not. The coin needs a certain amount of energy to extricate itself, to remove itself from the table. The electron needs energy to get away from the atom it's connected to. If I want to remove this thermos from this table, would you agree it's attracted to the table? Well, it's attracted to the earth, and the table is in the way. If I give it this much energy, does it move? No, I have to give it enough energy to leave the table. And that means that some of the photons that absorbs are absorbed by some of these electrons may not have enough energy to kick the electrons out. The energy that the electron needs to remove itself from the metal is called the work function. And before I forget, whenever you try to explain this on paper or in your head, avoid the use of the word pronouns. Pronouns in science are useless. Don't say it. You say it, if I'm having a conversation with you and you say it, I don't know what you mean, the electron or the photon. It, in this context, is the electron. The electron has to use some of the energy given to it to remove itself from the metal. And that energy is called the work function. The work function of sodium is very little. The work function of copper is more. The work function of platinum is huge. Okay. I'm not going to go through an explanation of this. I've discovered over time, and I have to change my notes, that it's not worth it. It turns out that if you take Planck's constant times the threshold frequency, you get that magical energy called the work function. And I can explain this to you in a very roundabout way. There's no need to write it down. That if you get a bigger energy than the work function, then you are using a frequency bigger than the threshold frequency. And this goes back to the beginning, that if the frequency is more than the threshold frequency, the electron gets kicked out. Right? I want to show you this graphic again. Right here. Remember this graphic? Other than the fact that I've lost my colors. Remember at the bottom, all I had was if the photoelectric effect doesn't happen, it's because the frequency used is smaller than the threshold frequency. You can look at your handout for this one now. Why is that? Because the photon energy is it's just this piddly little amount of energy. It's not enough to overcome the work function. So the photon frequency is smaller than the threshold frequency, and that results in a little itty-bitty drop of light energy being absorbed by an electron. And the electron gets it and goes, and it can't move. It's stuck to the metal. Whereas if I take a larger frequency, then I'm talking about a huge raindrop of light energy hitting the electron, and that energy is more than the work function, so the electron gets kicked off. We have one more thing to talk about here. Well, let's just explain some things first of all. If the photoelectric effect is happening, why would more light give you more electrons? We'll look at the bottom of the screen, which I hid from you before. Because brighter light has more photons. It's more light. More photons, more electrons. Current goes up. This one is trickier. Why, when you go to a higher frequency, do the electrons get more kinetic energy outside of the metal? The reason is this, and I'll just say it in my own words and then show it to you. If you go to a higher frequency, then the electron's given more energy. When it loses that little work function, it's going to have more left over. So if I go back to this diagram here, and I tell you maybe the work function, colors don't mean anything right now, maybe this is the work function. So an electron absorbs this violet photon, it loses that little sliver of energy and it gets to keep the rest. This is the work function. The rest would be the kinetic energy of the electron. This is the work function. The rest is the kinetic energy. There's more kinetic energy left over. So in your handout that I've given you at the bottom of this graphic, it says this is because each photon in the light will have more energy to give each electron. and therefore each electron will get more energy to keep in the end. As an analogy, and I don't know where I picked this up, if I thought of it or a prof way back in the day said it, you know, you're watching some movie where somebody is held prisoner in a corrupt country's jail, and they can get out of jail, they just need to bribe the guard. If the bribe is $100, or whatever imaginary unit of currency there is, if the bribe is $100 and I give them $20, do they get out? No, because they don't have enough to overcome the bribe. If I give them $101, do they get out? How much do they have when they're free? $1. And these electrons, by the way, are called free electrons. So there's a cost for these electrons' freedoms, and it's called the work function. I have one more thing that I'm going to do with you, and then you're going to have an assignment. I'm just going to explain to you the overall process here, and I have a feeling I'm missing something here. You have questions, right? You have a question 1?
And
2 I already did. 1 I've lost. Okay, so here is question 1. Write an equation relating everything that's going on here. Would you agree? Well, I'll ask you. This is for number 1. Question 1, midway through page 45. Would you tell me, think about, what is this the energy of in the photoelectric effect? What do you get when you calculate HF? Ian? No, it's not the work function. It's the energy of the photon before it gets magically absorbed by an electron. Is this, and you can write this down even though it's not complete, this is the energy of the photon. This is the kinetic energy of the electron. And I still haven't addressed the word max. Can you tell me why these are not equal? Jack's got it.
Because the kinetic energy is the leftover that is taken when it has to escape the metal.
Perfect. The kinetic energy is left over after the cost of freedom. So what do we have to do with the energy of the photon to find the kinetic energy left over? Subtract the work function. This is your conservation of energy statement for the photoelectric effect. And tomorrow I want to talk about it in a different way, but I think this makes a lot of sense to me. How much energy does the electron have when it's outside of the metal? How much was given to it, which is the photon energy, minus the cost of freedom, which is the work function. So this is how you're going to solve any photoelectric effect problems that involve calculations. And I realize this is a long lesson, but trust me, I've tried to break it up before and it just doesn't work. So hang in there, a few more minutes. But this can be found using a half mv squared, or it can be found using qv stop. This can be found using hf, or it can be found using hc over lambda. This might just be given to you in the question, or you might find it using HF0. And this formula, EK max equals QV stop, and this formula, work equals HF0, are on your formula sheets. They're in the top, I believe, right-hand corner under atomic physics. You have your work function formula there. You have your EK max equals QV stop. And you also have your formula for the photon energy. So what this means, everybody, is I could write, I'm not going to write it, I'm just going to verbally say it. I could write QV stop equals HC over lambda minus W. I could write QV stop equals HF minus HF0. I could write 1/2 mv squared equals HC over lambda minus W. You can calculate different components in this equation in different ways. But what's in brown is the basic idea. So before I tell you what I want you to have done for tomorrow, any questions about this equation? Ian?
For the HF, when we did that at the start of the lesson today, you could multiply the constant by frequency. Do we use the scientific notation?
I'm going to answer your question by saying you have to use the same types of units for every piece of this equation. So if you use 4.14 times 10 to the negative 15 for this HF, then you have to use electron volts everywhere. But these two formulas here on the left only work with joules. Okay? However, once again, if the stopping voltage is 2 volts, the electron has 2 electron volts of kinetic energy. You don't even need the formula. But if you use 1/2 mv squared, you're getting an answer in joules. So what your assignment is to complete examples 1 and 2, and that's why the answers are given to you here for these 2 examples. The answers are in brackets. And because this is a wild and crazy ride with all of these different formulas, you might get slightly different answers depending on the path you take. And you might decide to do one of these before the other or not. It's not necessarily you have to do them in the order given. So for tomorrow, you're going to complete example 1, example 2. Tomorrow we're going to go over them, and the rest of tomorrow's class is spent doing photoelectric effect problems. And then on Wednesday, we're going to finish the photoelectric effect because there's something else we have to talk about. All right, so you don't have much time left, but you might want to just get a quick start on setting up number 1 so that you're familiar with it when you take it home.